Put a machine in front of a human being and make it speak in perfect sentences. Watch what happens to the room. The voltage changes before the evidence does. People lean forward. Executives stop using cautious language. Engineers begin to use verbs that used to belong to minds. The machine understands. The machine reasons. The machine discovers. The machine knows. A waveform has crossed a threshold. Not in the machine, in us. The machine has emitted symbols in the correct order, with the correct pressure, at the correct moment. The output has the shape of thought, and once output has the shape of thought, the human nervous system wants to close the circuit. We supply the missing current. We see intention behind syntax. We hear understanding inside prediction. We treat a fluent signal as if it came from a mind, because for most of human history, fluent signals usually did. Richard Feynman would have noticed that conversion immediately. Not the computer first, the room. He would not have walked in with fear. Fear is too blunt an instrument for a physicist. Fear measures danger badly. It saturates the meter. It turns every unknown into the same red light. Feynman was not built that way. He liked tools, he liked machines, he liked strange mechanisms that could be taken apart, pushed past their rated limits, and made to fail in public. A machine that could generate language, code, images, molecular structures, and mathematical guesses would not have disgusted him. It would have pulled him toward the bench. But he would have asked one question: how do you know? Not as a slogan, not as a rhetorical flourish, as an instrument, a probe, a calibrated needle pushed into the insulation of a claim to find out whether current is actually flowing underneath. Because the first mechanism in artificial intelligence is not artificial intelligence. It is compression. A modern language model is not born with a small person inside it reading the world. It is built by feeding enormous volumes of text, image, sound, or code into a mathematical structure with adjustable weights. Those weights are not opinions, they are numbers. Billions or trillions of small knobs inside a high-dimensional function. During training, the system receives an input, produces an output, compares that output with a target, and adjusts the knobs by a tiny amount, again. A pump cycle repeated until the machinery can reproduce patterns that were previously distributed across the training material. The model is not storing the world in the way a library stores books. It is not storing sentences like files in a cabinet. It is bending a mathematical surface until, when struck at one location, it vibrates with the statistical echo of many previous examples. That is why it can feel so close to thought. Thought also compresses. Your brain does not store every photon that entered your eyes. It builds working models. It predicts. It fills gaps. It maps surfaces into shortcuts. If you see the front of a chair, your brain supplies the back of the chair without asking permission. Perception is not a camera, it is a prediction engine corrected by incoming error signals. So when a machine predicts the next token with enough precision, the output begins to resemble the surface behavior of a mind, not because the inside mechanism is the same, because the outside signal overlaps. That overlap is where confusion begins. A thermostat can control temperature without understanding winter. A camera sensor can detect light without understanding vision. A gyroscope can stabilize a drone without understanding balance. In each case, the device produces behavior that maps onto a human word: control, detection, stability. But the word is a loose adapter. It connects systems that are not internally equivalent. Artificial intelligence lives inside that adapter. When a model writes an explanation of gravity, it may be executing no gravitational intuition at all. It may be mapping one token distribution onto another. It may have learned that mass is curved spacetime, that acceleration is locally indistinguishable from gravity, that geodesics replace forces in general relativity, and that Einstein belongs near those sentences. The output can be correct. The structure can be useful, but usefulness is not yet understanding. Feynman would separate those wires. He would not say the machine is useless. He would say the measurement is incomplete. This is the first layer. Performance is not explanation. A machine can score well on an exam because the exam is a narrow channel. Inputs enter from one side, outputs leave from the other. The scoring mechanism checks the output surface. Correct answer. Incorrect answer. Pass. Fail. A benchmark is a pressure gauge attached to one point in a pipe. It can tell you something real. It cannot tell you the entire condition of the plumbing. A model that performs well on benchmarks may be genuinely powerful within that testing regime. It may also be brittle outside it. Shift the wording, change the distribution, remove a hidden clue. Ask for a chain of physical reasoning where the answer cannot be copied from textual residue. The needle can drop. This is not a moral failure of the machine, it is an engineering property of the system. Every system has an operating envelope, A jet engine has air pressure limits, turbine temperature limits, vibration limits, ingestion limits. A bridge has load limits, fatigue limits, resonance modes. A medical sensor has noise floors, calibration drift, false positives, false negatives. A language model has limits too: context limits, training distribution limits, alignment limits, retrieval limits, reasoning limits, calibration limits. The danger begins when the machine is sold as if it has none. Feynman hated that move, not because he hated optimism, because optimism without error bars is advertising wearing a lab coat. Now I want you to think about a product launch: a dark room, a screen, a graph moving upward, a narrator saying the system understands language, reasons about the world, assists medicine, accelerates science, transforms education, expands creativity. Each statement may contain a real signal. AI already does things that would have sounded like a technical fantasy a generation ago. It can search chemical spaces that no human chemist could examine manually. It can help predict protein structures from amino acid sequences. It can screen large image datasets for patterns. It can generate working code, draft text, summarize documents, translate languages, and search through noise for weak signals. That is real machinery. But Feynman would not let the upward graph do all the talking. He would walk behind the graph and look at the apparatus. He would ask how the dataset was built. He would ask what was excluded. He would ask whether the test examples leaked into the training pipeline. He would ask what happens when the input is damaged, adversarial, ambiguous, or outside the distribution. He would ask whether the model knows when it does not know. He would ask who benefits when the uncertainty is hidden. He would ask whether the error rate was measured on the easy cases or the cases that matter. He would ask for the failed runs. That is where the physics starts. A system is not understood when it works once under stage lighting. A system begins to be understood when its failure modes become predictable. When the engineer can say, below this temperature the rubber stiffens, above this frequency the circuit oscillates, beyond this pressure the seal leaks. Under this input distribution the model hallucinates. At this confidence threshold the classifier misses rare cases. Under this prompt structure the system becomes overconfident. In these languages the accuracy falls. In these populations the error rate shifts. That is knowledge with a boundary. No understanding. But there is a second mechanism operating at the same time: the black box. Black box is a phrase people use too casually, but it has a precise engineering smell. It means you can observe input and output, but the internal transfer function is not legible. You can send a signal in, you can measure a signal out. You can build a table of responses, but you cannot easily open the device and point to a single component that corresponds to the behavior. Modern neural networks are not black boxes because they have no internals. They are black boxes because their internals are too distributed for ordinary explanation. A concept is not stored in one transistor. A fact is not sitting in one labeled drawer. A behavior may arise from many layers, many weights, many nonlinear interactions, many statistical residues stacked into a working pattern. The machine has parts. The explanation is the hard part. This matters because science is not merely prediction. Prediction is one gear in the gearbox. Science also wants compression into principles. It wants to know what can be removed without breaking the result. It wants to know which variables matter and which are decoration. It wants to know whether the mechanism survives when the conditions change. A neural network may find correlations humans miss. That can be valuable. But a correlation is a signal. It is not automatically a cause. If a model predicts disease from medical images, it may be detecting a biological feature. It may also be detecting scanner type, hospital watermark, image compression artifact, patient positioning, or a socioeconomic trace embedded in the data pipeline. The output can be numerically strong while the mechanism is scientifically weak. That is the cargo cult failure mode. A runway made of bamboo can look like an airport from far away. It can have a tower. It can have headphones carved from wood. It can have men waving signals in the correct direction. The surface ritual can be copied. The airplane still does not land. AI can produce a similar illusion when the forms of science are copied without the discipline underneath. Graphs, benchmarks, technical language, confidence scores, leaderboards, demos, white papers, safety statements. The outer structure is there, but the core of science is not the outer structure. The core is the deliberate exposure of the claim to reality, the attempt to make yourself wrong before reality does it for you. Feynman called this scientific integrity, not politeness, not branding, integrity as a measurement protocol. You do not report only the trial that worked. You do not hide the conditions that make the system fail. You do not let the public believe the apparatus is more certain than it is. You do not call a statistical engine a reasoning engine until you have defined what would count as reasoning and built a test that can hurt your claim. That last part matters. A test that cannot hurt your claim is not a test, it is decoration. Now the story changes because Feynman was not hostile to computation. This is where the lazy version of the argument breaks. It is easy to turn him into a scold standing outside the future, shaking his head at machines. That would be false. He liked computers. He worked with computation when computation was still physically heavy, expensive, and primitive compared with what sits in your pocket. He thought about simulation deeply because physics itself forced the question. If nature is quantum mechanical, then simulating nature with classical machines has structural limits. He did not treat computers as toys, he treated them as extensions of experiment. In 1982 he published Simulating Physics with Computers. That was not a casual essay about gadgets. It was a direct attack on the mismatch between physical reality and ordinary computation. He saw that a universe with quantum behavior cannot always be efficiently represented by a machine built on classical assumptions. To simulate nature, the machine may need to use nature's own rules. That is not fear of machines. That is respect for mechanism. In his final years, he also spent time around the connection machine, a massively parallel computer built by thinking machines. When Danny Hillis described a plan for a computer with huge numbers of processors, Feynman reportedly called the idea foolish in blunt language. Then he got interested enough to work on it. That is the Feynman pattern. A crazy claim is not rejected by mood, it is dragged toward the bench. He did not ask whether the idea sounded grand, he asked whether the thing could be made, tested, and understood. That is exactly the attitude AI needs, not worship. Not panic. Benchwork. A large model is a machine made of statistics, optimization, data curation, hardware, human feedback, and social deployment. Each piece is a subsystem. The training data is the fuel. The architecture is the engine geometry. The loss function is the control signal. The optimizer is the adjustment mechanism. The evaluation set is the test rig. The user interface is the coupling between machine and human. The business model is the pressure gradient pushing the machine into the world faster than the test rig may be able to follow. Feynman would look at all of it. He would not stop at the neural network. He would inspect the institution around it, because institutions are machines too. NASA was a machine, not just rockets and O-rings, committees, incentives, reporting lines, schedule pressure, managerial language, risk estimates. Challenger failed physically, but the physical failure passed through an organizational circuit before it reached the sky. An O-ring at 32 degrees Fahrenheit is not philosophy. It is rubber losing resilience in cold conditions. But the disaster was not only rubber. It was a gap between engineers who knew a danger and managers who processed risk through a different control system. Feynman's ice water demonstration worked because it collapsed a complex institutional fog into a simple physical fact. Cold rubber did not rebound correctly. The seal was compromised. The claim met the bench. That is what he would try to do with AI. He would look for the ice water. For a medical AI system, the ice water might be a dataset from a different hospital, different scanner, different patient population, different lighting condition, different disease prevalence. For a language model, it might be a question whose answer is not common on the internet, a problem with a false premise, a request where the correct behavior is to stop and say the input is insufficient. For a hiring algorithm, it might be a bias audit where protected attributes are removed, but proxies remain. For an educational AI tutor, it might be a student who gives confused work, not a clean question. For scientific discovery, it might be a prediction that must survive wet lab replication. The public demo is not the test. The failure case is the test. And this is the third mechanism, the human tendency to confuse fluency with authority. Fluency is a dangerous output because it reduces friction. A rough machine makes you suspicious. A smooth machine lowers your guard. If a system produces broken grammar, you inspect it. If it produces polished paragraphs, you begin to lean on it. The surface finish changes the user's trust before the truth has been measured. This is not unique to AI. Humans have always trusted confidence too much. A person who speaks smoothly can pass as more knowledgeable than a person who pauses to think. A polished chart can feel more scientific than a messy table of raw measurements. A clean interface can make a fragile system feel mature. Presentation acts like lubrication in the trust mechanism. It reduces the resistance between claim and belief. AI adds a new kind of lubrication. It can produce the surface features of competence at industrial speed. That speed matters. A human expert can be wrong, but a human expert is bandwidth limited. A model can produce wrong answers at the speed of electricity and with the tone of certainty. It can generate thousands of plausible explanations, legal summaries, medical suggestions, code snippets, historical claims, and scientific hypotheses before a human reviewer has finished checking the first one. The error does not merely exist, it scales. Scale changes the physics. A single loose bolt is maintenance. 10,000 loose bolts is a system hazard. A single hallucinated citation is embarrassing. Millions of hallucinated citations moving through search, education, and media become contamination in the information supply. The machine does not need malice, it only needs throughput. Feynman would notice the throughput. He would also notice the asymmetry. Generating a plausible answer can be cheap, verifying it can be expensive. That is a thermodynamic problem in the economy of attention. The machine emits low-cost symbols. The human must spend high-cost judgment to test them. If the system produces more claims than society can verify, uncertainty accumulates like waste heat. This is why the central question is not whether AI can answer. The central question is whether the answer is connected to a reliable checking mechanism. A calculator has a narrow domain, but inside that domain, it is tightly coupled to arithmetic rules. A thermometer has a physical sensor calibrated against known standards. A GPS receiver triangulates signals from satellites with known clocks and orbital parameters. These devices can fail, but their failure modes are constrained by physical or mathematical coupling. A language model's coupling to truth is looser. It is coupled to patterns in data, human feedback, retrieval systems, tool use, and sometimes external verification. That coupling can be strengthened. It can be engineered, but it should not be assumed. A model that sounds right is not a voltmeter. It is a signal generator that may or may not be connected to a measurement circuit. That distinction is the whole machine. Now the evidence calibration, AI systems do have measured capabilities. AlphaFold is the cleanest example because the problem domain has a strong external structure. Proteins are not opinions. They fold into three-dimensional shapes constrained by chemistry, geometry, evolution, and thermodynamics. A prediction can be compared to experimental structures. Error can be measured in angstroms. Confidence can be mapped. The model can be wrong, but the world pushes back. That is why AlphaFold matters in this story. It is not powerful because someone called it intelligent. It is powerful because it inserted prediction into a domain where reality can check the output. The machine produced structures. Scientists compared them. Researchers used them. The database expanded to over 200 million predicted protein structures. The signal met a measurement frame. Feynman would respect that. He would still ask where it fails. He would ask which proteins are disordered. Which complexes are harder, which interactions require caution, which predictions should not be treated as experimental structures, which confidence scores are reliable, which biological conclusions require wet lab confirmation. He would not dismiss the machine. He would keep the ground wire attached. That ground wire is reality. Language models are harder because language floats. A sentence can sound true without touching reality at any point. It can be coherent and false. It can be helpful and ungrounded. It can contain a correct equation inside a wrong explanation. It can cite a paper that does not exist. It can solve one problem and fail a nearby problem because the local pattern changed. The output is not meaningless. It is unstable unless checked. This is the layer many people do not want to discuss because it slows the story down. Investors like acceleration. Companies like adoption. Media like spectacle. Users like convenience. Institutions like automation. The machine promises lower cost, faster throughput, fewer bottlenecks. Doubt becomes friction. Feynman would insist on friction. Not the friction that blocks discovery. The friction that keeps the wheel from slipping. There is a difference between a brake and traction. A brake stops motion. Traction makes controlled motion possible. Scientific doubt is traction. It lets power become useful instead of merely fast. Without doubt, AI becomes a high-torque motor on a low-friction surface. It spins, it makes noise, it looks energetic. It does not transmit force cleanly to the road. The deeper problem is that AI sits at the boundary between instrument and authority. A microscope extends vision. A telescope extends vision. A particle detector extends sensation into regimes the body cannot touch. These instruments do not replace reality. They mediate it. They have calibration rituals, control samples, error estimates, noise models, blind analysis, replication. Peer review. The point is not to make the instrument look impressive. The point is to know exactly how the instrument lies. That sentence is the scientific instinct. Know how the instrument lies. AI must be treated the same way. A model is an instrument that lies in specific ways. It overgeneralizes, it interpolates, it confabulates, it absorbs bias, it hides uncertainty behind fluency, it can optimize for the test rather than the world. It can exploit patterns that are predictive but not causal. It can generate explanations after the fact that sound like reasons, but function like decorative covers over a black box. Once you know how it lies, it becomes more useful. This is not anti-AI, it is anti-hypnosis. Feynman's suspicion was never aimed at machinery, it was aimed at self-deception. The easiest person to fool is the person building the system, funding the system, selling the system, or wanting the system to be true. AI amplifies that danger because the outputs are seductive. They arrive polished, they arrive quickly. They arrive with the tone of a system that has done the work, but the tone is not the work. The work is still the checking. A physicist does not ask a theory to sound elegant. A physicist asks where the theory breaks. A bridge engineer does not ask whether the bridge rendering looks stable. The engineer calculates stress, fatigue, wind loading, material defects, thermal expansion, and resonance. A rocket engineer does not ask whether the launch presentation looks confident. The engineer asks how cold the rubber was. AI needs that same culture. The question is not whether the machine can produce an answer. It can. The question is whether the machine can expose the path between input and answer in a way that lets another system test it. Sometimes the answer will be yes. In constrained domains with strong external validation, AI can function as an accelerator. It can search a parameter space, generate hypotheses, reduce manual labor, and point human attention toward promising regions. It can act like a fast pump moving fluid through a large pipe network that used to require hand pressure. But acceleration is not navigation. A faster pump can flood the wrong chamber faster. A faster search can generate more false leads. A faster writer can produce more unverified text. A faster classifier can automate unfairness at scale. A faster scientific engine can make correlations look like causes before anyone has paid the cost of replication. Speed has no ethics. Speed has no epistemology. Speed is a magnitude. Direction must be supplied. Feynman would have been especially allergic to one phrase, the AI knows. Know is a heavy word. It implies a relationship between representation and world. It implies that when conditions change, the representation deforms correctly. It implies that error can be recognized. It implies that the system has some grasp of the constraints behind the answer, not just the surface pattern of the answer. A model may contain useful representations. It may encode grammar, facts, visual features, mathematical regularities, chemical structures, and programmatic patterns, but whether that deserves the word know is not decided by the smoothness of the output. It is decided by tests that distinguish imitation from mechanism. A parrot can reproduce sound, a child can use language, a calculator can multiply, a physicist can derive. Each produces correct-looking symbols under some conditions. The internal machinery differs. The test must separate the machines. If an AI system says a ball rolling down a ramp accelerates, can it apply the same principle when the ramp is inside an accelerating elevator? If it explains Ohm's law, can it diagnose a circuit with a hidden short? If it writes code, can it reason about a race condition that appears once every million cycles? If it recommends a treatment, can it state the population on which the evidence was measured, and the population where the evidence may not transfer? These are not trivia questions, they are load tests. A load test does not ask the bridge to look like a bridge. It loads the bridge. For Feynman, understanding had a constructive flavor. To understand something meant you could rebuild it, or at least rebuild the essential mechanism in your head. You could strip away ornament, you could derive the behavior, you could predict where the structure would fail. On his blackboard near the end of his life, there was a line that compresses this instinct. What cannot be created has not been understood. That line cuts directly into AI. If we cannot create the explanation, we should be careful when we accept the answer. But the line also cuts the other direction. If AI helps us create new explanations, if it helps us find mechanisms, if it helps us design experiments that expose hidden structure, then it becomes part of understanding rather than a substitute for it. The danger is not the machine doing work. The danger is the machine replacing the part of work where reality is allowed to object. Science is not a factory for confident sentences. It is a system for making reality interrupt us. That interruption is sacred in the mechanical sense. It is the feedback signal without which the controller runs open loop. An open loop controller cannot correct itself. It sends commands based on an internal plan and never measures the output. If conditions change, it fails. Closed-loop control measures the result and adjusts. Science is closed-loop knowledge, hypothesis, experiment, error, revision. The loop is the intelligence. AI without verification is open-loop language. It can still be useful. Open-loop systems can work in stable conditions. A toaster does not need a camera to toast bread. But the more complex and variable the environment becomes, the more dangerous open-loop control becomes. Medicine, law, education, science, finance, and public information are not toaster environments. They are noisy, adversarial, high-dimensional human systems with feedback delays and hidden variables. Deploying AI there requires more than accuracy claims, it requires instrumentation. The model needs logs, audits, calibration curves, independent test sets, red team failures, bias measurements, confidence behavior, domain boundaries, human escalation points, post-deployment monitoring, mechanisms for appeal, mechanisms for correction, mechanisms for saying the machine is outside its operating range. That is not bureaucracy. That is engineering. A pressure vessel without a relief valve is not elegant because it has fewer parts. It is dangerous because it has removed the part that admits pressure can rise beyond design. AI systems need relief valves. They need places where uncertainty can escape instead of being compressed into false confidence. The public does not usually see those valves. It sees the polished interface, a text box, a button, a voice, a response. The machinery disappears behind convenience. And when machinery disappears, authority increases. The user cannot see the gears, so the output feels like an oracle. Feynman would have despised the oracle, not because oracles are wrong every time, because an oracle cannot be cross-examined as a mechanism. It speaks, the listener submits. Science is the opposite relation. The claim submits. Reality cross-examines it. AI should be placed on the table, not on the altar. Now think about the phrase artificial intelligence itself. It compresses multiple machines into one dramatic label. A recommendation system, a protein folding predictor, a language model, an image generator, a robotic control policy, a fraud detector, and a theorem prover are all placed under the same umbrella. This is convenient for headlines and bad for understanding. The mechanisms differ, the risks differ, the tests differ, the meaning of success differs. Feynman would split the umbrella apart. He would ask, which system, trained on what data, optimized for what objective, evaluated by what metric, deployed in what environment, affecting which humans, with what failure cost? That sentence is not catchy, it is useful. The question nobody wants to answer is not only how do you know, it is how do you know in this exact case. Because truth is local to the apparatus. A measurement is not floating in the air, it belongs to a method. A thermometer reading belongs to the calibration of the thermometer. A telescope image belongs to the optics, the sensor, the exposure, the processing pipeline. An AI output belongs to the training data, architecture, prompt, retrieval context, safety layer, tool access, and evaluation protocol. Remove the apparatus, and the claim becomes vapor. This is why Feynman's attitude would feel harsh in an AI boardroom. He would not be satisfied with words like transformative, revolutionary, human level, autonomous, or general. Those are not measurements. They are pressure waves in the air. He would ask for the meter. He would ask for the error bars. He would ask for the cases where the system failed, and what changed afterward. He would ask whether the people presenting the system tried as hard to disprove its competence as they tried to display it. That is the part nobody wants, because a beautiful demo is a one-way valve for belief. It lets excitement flow forward and blocks doubt from flowing backward. A failed demo breaks the valve. An honest failure table breaks it even more. It forces the audience to see the machine as machinery again, and machinery is what it is. A very large, very useful, very unstable, very powerful arrangement of data, silicon, optimization, and human desire. The desire is not a side issue, it is in the circuit. People want AI to be a mind because minds are expensive. Minds require training, payment, sleep, ethics, context, and resistance. A machine that appears to think promises obedience without fatigue. It promises expertise without apprenticeship. It promises creation without waiting. It promises judgment without responsibility. That promise is thermodynamically suspicious. You do not get ordered output for free. Somewhere cost is paid. In data collection, in human labeling, in compute, in energy, in hidden labor. In error correction, in social risk, in the future cost of mistakes made at scale. The machine may reduce one cost by moving it elsewhere. That can still be worth doing, but the accounting must include the whole system. Feynman would widen the diagram until the hidden wires appeared. He did that with science itself. The value of science to him was not only its ability to produce tools, it was the freedom to doubt. A civilization that gets powerful tools without the discipline of doubt holds a key that can turn both ways. The same machinery that accelerates medicine can accelerate misinformation. The same system that helps a student can weaken the student's ability to struggle with a problem. The same model that helps a scientist search can flood the literature with low-quality claims. The same automation that reduces cost can make accountability evaporate. The key turns both ways. That is not a reason to throw away the key. It is a reason to stop pretending the key only opens one door. This is where fear becomes useless again. Fear says stop. Hype says go. Feynman would reject both as primitive controls. Stop and go are not enough for a machine this complex. You need throttle, steering, brakes, sensors, diagnostics, maintenance, and a driver who understands the road conditions. AI should be advanced, but it should be advanced with instruments attached. The most Feynman-like AI lab would not be the one with the loudest demo. It would be the one with the best failure museum, walls of broken prompts, misclassified images, false citations, failed protein predictions, bias audits, edge cases. Distribution shifts, near misses, reproducibility reports, cases where the model looked confident and was wrong, cases where it looked uncertain and was right, cases where a benchmark improved and real-world performance did not. That museum would be more valuable than another launch video, because failure, properly measured, is information with teeth. Success can flatter you, failure can teach you the shape of the machine. Now return to the room where the AI speaks. The sentences are still smooth, the graph still rises, the demo still works. None of that has been erased. The machine may still be useful, it may still save time, it may still help science. It may still open regions of search that human beings could not explore by hand. It may still become one of the most important instruments ever built. But the air in the room should feel different now. The output is not the understanding. The benchmark is not the world. The interface is not the mechanism. The confidence is not the calibration. The answer is not the experiment. Feynman would not fear the machine. He would put it on the bench, cool the rubber, bend the input, break the demo, check the wiring, publish the failures, and ask the same question until the room stopped applauding and started measuring. How do you know? That is not resistance to the future. That is how the future stays attached to reality.